everyone. Welcome to Digital Media E10. This is Exposing Digital Photography, and I am Dan Armendariz. We have a wonderful semester in store for you, and I am very excited that you are all here, whether you're joining us here in person or at a distance. We've had numerous iterations of this course in the past. We've had it at the Extension School starting in 2007 when it started in the Computer Science Department, and that was under E7. That was local for the entire time. Then I actually moved out of the state and had it in a sort of a trial run at UC Berkeley, and it was sort of a lot of fun to see the very different styles of photography that we would get out there. But now we're back, now we're online, and hopefully you will find it as enjoyable and as interesting as ever. So the way that I usually start out with this class is to actually take a picture, and as a matter of fact, today's going to be no different, so be sure that you smile. But don't worry too much about the fact that you're on camera, because frankly, we're not going to be able to identify you in this particular picture. The reasons for that are manyfold, and we'll actually discuss that as time goes on. But this is, in essence, a pinhole lens, and this can be made in a variety of ways. You can go home and you can create one on your own. In fact, this one is sort of the first one that is a little bit high-tech. So at the office, we just so happen to have a 3D printer, which can take, you can create an object in a CAD program on the computer, send it to this printer, and it will actually print out very fine, very thin layers of plastic, one layer at a time, eventually creating whatever was the object that you had created. In this case, I didn't actually create this object in the computer. Fortunately, there's also a website where you can go find all of the many creations that people have created. And it just so happens that somebody created this object called a body cap. And a body cap is basically just a piece of plastic that many cameras come on the front of them in order to protect the camera body itself from disaster, from problems. And this is particularly relevant if your camera doesn't actually have a lens attached to it. You might be familiar with the term lens cap, which is the same idea, but it covers a lens instead of the camera body itself. So this really is only relevant to these types of cameras where the lens can be removed. Now, this is actually kind of interesting that we're able to print this, because as I'll pass a couple of these around, and you can, if you would be so kind as to just take a look at it and sort of pass it around to your neighbors, you'll notice that it's kind of an intricate design in that there are some threads in order to actually screw it into the body of the camera. And so this is actually a picture that I took today of the 3D printer actually printing the body cap. And there's two of them that are floating around right now. One of them is an orange body cap, which is just a standard Canon EF body cap. This is one of the real ones, just by comparison. This is not a 3D printed one. And the one that we printed today was black. One of the orange ones was just a test that we had printed just to see how it was going to go. I tried to take a picture using a prior pinhole lens that was printed in orange and found that it was, unfortunately, a fair amount translucent. So the whole image was just orange. It's just ridiculously orange, but we were able to resolve that by changing it to black. So now we printed it in black. Now the black one that's actually floating around, there's an interesting story behind that. That was going to be the original pinhole. That was going to be the one that we were going to use in class, and somebody decided to help out with my project, and he offered to make a little hole in the middle, and he took a knife and he put it right through, and unfortunately it didn't create a hole, it created an entire gash. So that one's out of commission. If you take the tape off of that black one, you'll actually see the enormous gash underneath. So we decided to redo it, and you can create your own. And the way that you can do this, you don't have to have a 3D printer. You just need to have a body cap that you can buy, and generally you can buy extras of these on Amazon or from your camera manufacturer's website directly. Drill a hole in the center, make it a fairly large hole, because in order for you to create a really fine hole, you have to do any number of things. One of them, and the one that we're using, the method that we used here, is to take some aluminum foil, tape it to the front, and use a needle to point just the tiniest little hole in the aluminum foil. So how is this image going to come out? We'll have to find out in a little bit. One of the interesting things about this is that it also is, there's multiple versions of this pinhole, and this one I think is not quite as good as one that I had made prior. I think my threading skills are not quite up to par as they might have been. So let's use this. Let's take this and just keep it in mind for a little bit. This is sort of an example that we're going to use throughout the next couple of weeks as a way of discussing some aspects of digital photography, especially as related to exposure. Let's take a step back for a minute and talk about cameras themselves. So there's a wide variety of styles of cameras. There's many different types of cameras that are available out there. And one of the ones that you'll see very frequently, and perhaps you may already have, or you may be very interested in, either as a result of taking this class, or maybe the interest in taking this class is the result of you having one of these types of cameras. But these sorts of cameras, single lens reflex cameras, are so named because of their construction. And we'll look at their construction in just a little bit. But essentially, there is a mirror inside that flips up out of the way. It's a single reflex, and it allows you to swap lenses on the front of it. Now, there's a variety of different types of cameras that allow you to do this as well. But these are traditionally known as sort of the ones where a layman might refer to it as a professional camera. They might say that this is a very professional camera. You have some very big lenses perhaps associated with it. So we might have, oops, I know I disappeared for just a second. Might have some big glass like this, which is very different from a lens that you would have on a much smaller camera, for example. But some of the power that comes from these cameras is, in fact, their size. It is not only the size of the lenses, which for physics reasons do actually help some of the properties of that lens, as we'll talk about in future lectures, but also it helps the size of the camera. Bigger cameras tend to have a variety of different properties. Can anyone suggest any reasons why a bigger camera might be better? Any reason at all? Yeah. More light allowed into the sensor. So that's a very good reason. That is certainly true, especially if the sensor itself is also made larger by the fact that we have a larger camera. One of the things that we find nowadays also is that a lot of cameras are shrinking in body size, but enlarging in sensor size. So that's an interesting development in some of the latest technology. But are there some other reasons why we might want to have a larger camera? Yeah.
Better mechanical elements, like for more shutter speed?
So, right, so we could have more robust components. So in this case, there are some mechanical devices within this camera that actually allow it to function, that actually move the mirror out of the way and expose the sensor to light that's incoming. Larger cameras might be able to have more robust mechanics so that they don't break as easily. Also, the internal structure itself might be slightly more robust. It might have a magnesium alloy frame or titanium frame inside, and so that it's more resistant to drops. Or they could also add some gaskets, some rubber gaskets, so that it's more resilient to weather, for example, to rain, to dumping it into the ocean, which has happened a couple of times, and a variety of other things that you might throw at your camera. Any other reasons? Yeah. More detail in what way? Oh, in the image itself, in the resulting, right. So you can certainly get more detail. So this also, I think, can allude to the fact that in larger bodies, it's easier to have larger sensors as well. So some of the reasons that I think having a larger camera are great is that it also means that you can have an enormous battery inside of it, and the thing will last forever. Now, there's other reasons why SLRs typically have longer battery lives than some other cameras, and we'll discuss those as time goes on. But typically, these cameras do have longer battery lives. And one of the reasons is that, well, the batteries can just be larger. The other one is ergonomics. These cameras have generally enormous grips that make it very easy for normal, or for our hands really to grab them. There's a variety of camera sizes, and the smaller ones typically are kind of difficult to hold. And I think that these certainly help out with that as well, and that can certainly help with a variety of other things related to ergonomics, such as better button placements. It makes it a lot easier for the manufacturers to place buttons directly underneath your thumb or directly underneath your index finger, make all of those features and all of the functions available within to you much more easily. And also, of course, they can cram in more electronics. They can put more features, for better, for worse. They can add a lot more stuff, including this larger battery. Now, there's a lot of other cameras, and there's a lot of other types of cameras, and I don't want to ever give off the impression that I think that SLR cameras are the way to go in photography. In fact, for many years, I had a Canon SLR, very much like the one that's set up as the demo right here. But recently, 2 years ago, I dumped the Canon system entirely in favor of a different type of camera called mirrorless. Mirrorless cameras have a lot of the same advantages of SLR cameras. For example, they are interchangeable lenses. They support interchangeable lenses, meaning that you can create, or rather you can buy lenses that are very high quality and also have a very high price tag and be able to swap them out. Or you can upgrade your lenses as you go on. You can get lenses that offer a variety of different features, very small lenses that offer limited features but have a lot of portability, for example. This was very important to me because I found that there were a few types of lenses that I really used, that I was really interested in using, but I wasn't going to get those options if I had just a fixed lens camera. Now, mirrorless cameras also have a variety of other advantages. The body size is much smaller because they don't have to have the mechanics of actually lifting the mirror out of the way, hence the name mirrorless. But they do have some disadvantages as well. Because they are smaller, the sensor tends to be a little bit smaller. This can reduce some of the quality that we've been talking about, that we can actually get, the quality and the light gathering capability that we can get out of these larger sensors. However, of course, that's not always the case. Some of these mirrorless cameras actually have enormous SLR-sized lenses inside of them, and those are special cases, though. The battery tends to be a little bit less. It's not quite as good just because, again, the body's a little bit smaller, and it has to, the battery has to be a little bit smaller. But also, for many of these cameras, as we get smaller and smaller in size, many of these cameras don't have a very notable feature of the SLR. The SLR camera has that very distinguished feature of the pentaprism at the very top of it. If you have an SLR camera, the way that you take a picture is you look through the viewfinder and take a picture. Now, not all mirrorless cameras have that, because in an effort to be compact, they will get rid of that altogether and rely on the LCD screen on the very back of the screen, or on the very back of the camera, for framing and for exposure and for doing all the things that you would do with the camera. Using this screen is very taxing and is very expensive on the battery, and is one of the many reasons why some of these smaller cameras just do not have as good battery life as the SLRs. Now, we can keep going down in size, of course, as we move away from mirrorless cameras. Then we get to compact cameras. And now there's even a new class of cameras called bridge cameras, which have the appearance of SLR cameras, or these larger, more professional, quote-unquote, cameras, because it looks like they have a very large lens attached to the front of it. It looks as though they have a viewfinder up top. But in fact, they do not have the lens box. They do not have the mirror box, the means to actually move the mirror out of the way. There's no mirror actually associated with it. The lens is fixed. Basically, any camera that has a fixed lens and is relatively small, I would sort of consider under this compact and bridge designation. And of course, there is the very popular camera phones and smartphones. Now this, I think in years past, we'd talked a little bit about how, well, this is certainly a very legitimate way of taking photos and taking excellent photos, but now more than ever are we finding that the cameras in these very small devices are getting very good. The sensors are getting very good in them. The lenses are getting very good, even though some of the lenses are frankly made out of plastic, which is kind of surprising. But still, the technology is improving, and it's getting to the point where we can use cameras in somewhat professional or even very professional settings. For those of you that follow social media, if you have an Instagram account, for example, there's a couple of Instagram accounts that are very popular. For example, Nat Geo, so National Geographic has an Instagram account, and they will occasionally post photos from their photographers that journey around the world taking photographs using smartphones. They use smartphones and they post it on Nat Geo, and they're amazing photos. So just because you are using a small camera doesn't necessarily mean that you have reduced capability to take photos. But one of the interesting things, and what is the thing that I really want you to take away from this discussion, is that all of these cameras have compromises. Sort of the major distinction that we're making between all of these in classifying them is primarily based on their size. So SLRs, for example, we first described as being big and bulky, the professional-looking ones, because everybody knows you're taking pictures. They have the capability to change lenses, But even iPhones and smartphones these days have adapters where you can snap on other lenses on top of them and get other views from that same camera, which is interesting. It does reduce the quality a little bit, but it does provide a proxy for this same capability that we have in these much larger cameras. But other than size, there's so many other features that we have to take into account. So battery life, for instance, or the fact that it's a dedicated camera. So iPhones and other camera phones and other smartphones do not necessarily have the same capability in terms of the control over the exposure that we might find in these larger cameras. And there is something to be said as well about the size of the sensor inside. The larger sensor sizes for the same technology, for the same era of technology, will generally be much higher quality than those of smaller sensor sizes, or those smaller sensor sizes. This is really just sort of a matter of physics, and again, we'll talk more about this later on as we get closer to talking about digital cameras specifically. Now, moving on, some of the stuff that we're going to talk about is in fact related to single lens reflex, SLR cameras. In the past, we've noticed that a lot of the students in this course do come in or have an interest in SLR cameras, and it's very interesting to talk about this for a number of reasons. One, it is actually very useful to talk about this, especially for those of you that come into this class with a background in film, but not necessarily a background in digital. This will sort of help bridge the gap between film and digital. But also, it's very interesting to talk about these cameras because very often it is true that these cameras are considered the highest end range of cameras that we can talk about. So if we talk about what features these cameras have, we can also talk about what of these features other cameras do not have and sort of continue classifying them as a result. So this is an internal side view of an SLR camera. Basically what we are seeing is item one is a lens, essentially. We can see some light entering through the lens. It's being focused, reflected off number two, which is in fact a mirror, which then reflects the light up and through the pentaprism. It bounces around in the pentaprism in item 7 before actually shining through the viewfinder in number 8. And that's when you can compose your shot, take the image, and so on. But what's very interesting is when we actually press the shutter release, it moves the mirror out of the way. Number 2, the mirror flips up out of the way, and the light then shines to the very back, which houses the sensor or the film, and the shutter and the exposure is taken. Now, what does this mean, of course, for the light that was reflected and going up through the viewfinder and into your eye? This light is actually no longer shown. So as soon as you push the shutter button, the mirror moves up out of the way, and then you no longer actually see the light that you were previously seeing. So this is one of the measures of the performance of an SLR camera is, in fact, how long is the blackout time? How long is this amount of time between when the mirror moves up and out of the way, the shutter opens and the sensor plane is exposed, the shutter then closes, and then the mirror moves back down. This is a number of mechanics that have to happen in order for this image to actually take place. And so there is one important mechanism here as well, which is item number 3, which is the shutter. So there is this idea that we have this mirror, which in this case is a fully reflective mirror. It takes all of the light incoming through the lens. It reflects the light up into the pentaprism, into the viewfinder. So an interesting question is, why do we have to have this additional mechanism behind the sensor to block the light? Essentially what is happening is the mirror moves up out of the way, and then there's this other mechanism called the shutter that continues to block the light. So why do we have these two separate devices to do it? Why don't we just have the mirror move up out of the way to expose the film in the very back and then close the mirror, or rather reset the mirror to shut off that light, so to speak, that is being sent to the sensor? Any ideas why we have to have two separate mechanisms? I'm sorry? Yeah, so you can control the time. So imagine the weight of this mirror. It may not be very much, but imagine of the weight of this mirror compared to the mass of the camera. It's perhaps a reasonable percentage of that mass. This is quite a lot of mass for the camera to have to move up out of the way, and it's not going to do it in a very precise way. Some of the more advanced, some of the higher-end SLRs will do this in a very precise and a very sturdy and reliable way, but those require a lot more engineering, basically, in order to make it reliable and to make it robust. But even so, this is a lot of mass that has to move up out of the way, and then for the camera to move back down to do it in a precise enough way to give us the shutter speed that we actually want. So many of these cameras have shutter speeds which are exceedingly fast, 1/8,000th of a second or so, and moving the mirror up out of the way and back down is a tall order for 1/8,000th of a second. But there's another reason as well, and that is that the mirror moves in a symmetric way. It moves up first, and then it moves back down. So what this means is that in that time, we move the mirror up out of the way, light starts shining to the bottom part of the sensor first. And then as it actually moves up, it will then start to move back down, and then that bottom part of the sensor will continue receiving light until the very end. So you would then get an uneven exposure. You would have variable amounts of light. You would have the bottom part of the sensor which receives the most amount of light just in the movement of this mirror, and you would have the top part of the sensor which receives the least amount of light. So what this would look like, if you imagine what a camera what an image that would look like coming out of a camera like this would be bright at the bottom and dark at the top. Actually, it's a little bit of a lie. It's actually the other way around. It's upside down, but we'll talk about that in a later lecture. And that's actually one of the things that you'll find out about this class is that all of these things are interwoven. We have to start somewhere, of course, but a lot of these ideas are interwoven, and there's going to be a lot of teasing that goes on. I will say, I'll give you a little hint, and we'll talk about this in a few weeks. We'll talk about this in a few weeks. Don't worry, we will get to it. I'm not punting all of these explanations, but we can't explain everything all at once. We have to abstract away some of these things, and we'll get to some of those nitty-gritty details at a later point in time. All right, so what we would have in this case is a couple of things. First, we would have an image that was bright on one side and dark on the other. We would also have an imprecise shutter speed, so the solution is to have a shutter, this object number 3, that actually opens and closes. It's much lower mass, and it actually exposes the sensor in an even way to the light. So it fixes both of these problems at once. And essentially, it's made out of plastic, or some really fancy ones made out of like Kevlar materials, really strong, very light materials that the motor can move quickly along the plane of the sensor. Now, there's a variety of types of shutters. Some of them will move up along the vertical axis. Some of them will move along the horizontal axis. Some will actually open like leaves, like that. It's pretty neat. But all of the SLRs that we have nowadays are ones that move along a certain plane. They don't have a leaf style of mechanism. So this is actually a very interesting thing. We have to do all of this mechanics in order to actually take this photo. And if you've ever used an SLR, you know that this happens very quickly. And in fact, moving the mirror out of the way and opening the shutter and then closing the shutter and then closing the mirror again gives that SLR its very distinctive sound of taking a picture. That one of, well, let's see, I can only do half of it right now because of the way it's set up, but open. Oh, I have to wait 20 seconds. Okay, let's see if I can time this well. So how does this actually look? You may have tried to look at your camera as it was actually taking a picture. I have here some high-speed footage that I borrowed from the internet that actually shows this very thing. So what we are looking at is an older Canon 5D camera. I believe the original one. This is the one that we have here is one of the newer models. And you can see that the lens has been removed from the front of it so that we can see the mirror. And what's interesting is that you can actually see reflected in the mirror, you are seeing the pentaprism, that sort of gray box. You're seeing the pentaprism, but in reality, what you're actually seeing is the object that's behind the viewfinder. The light that's reflecting off the wall behind is coming in through the viewfinder, reflecting around the pentaprism, coming back down and reflecting off the mirror and into this camera that took this photo. So you're sort of seeing the reverse of what we normally do. This is this object right here, this sort of overexposed gray. It's supposed to be gray. This overexposed area is called the mount. It is where you actually attach lenses to the camera. You can see a couple of electronic contacts that provide power to the lenses for focus or for image stabilization. All of these things are things we'll talk about, of course, at a later date. So what actually happens when we push the shutter button and lift the mirror out of the way? Mirror lifts up. There's, what is this in the back? The shutter itself. And you could actually, did you see it move along the film plane? So let's do it again. Just to sort of give you a, why isn't this going? All right, here we go. Push the button. Mirror moves up out of the way. That's the shutter. Now we can see the shutter open, and then there's another shutter that closes behind it. Now, as you may have been able to tell, I've already oversimplified some of the things here. So let's talk about some of the other things that we've talked about that I didn't yet have a chance to mention. One of them is that there's not just one shutter, there's these two shutter pieces. There's one shutter that opens and actually exposes the sensor, and then there's another shutter that closes behind it. In actuality, we call the combination of these two things the shutter, but we distinguish them by calling the first object the first curtain. It's basically just a curtain that opens. Then we call the second object the second curtain. So the first curtain opens first, the second curtain follows behind it. Now in this case, we also saw something else. When the mirror flipped up out of the way, did you notice anything else unusual? Let's see, right there. This object right here. Looks like another mirror, right? But that's weird. I described to you how there's this one mirror that reflects the light coming in from the lens up into the pentaprism, reflecting around the pentaprism and out the viewfinder so that you can actually see it. So what is this other mirror actually doing for us? Any ideas? Metering? Yeah. Anything else? We'll talk about metering in just a moment. Yeah. It does. It is still. So at this point, it would not be showing it because the mirror is moving up out of the way, so nothing would be reflecting up. But you can imagine where that original mirror was placed originally, before we actually pushed the shutter button. If we switch back to the slides here, the mirror that we have is actually at a 90-degree angle to mirror number 2. So it's pointed like this, and it's pointing the light down into the body of the camera. So the mirror that we are dealing with, mirror number 2, is not actually a complete mirror. It doesn't reflect 100% of the light. It allows some light to pass through and hit this secondary mirror. There's a secondary mirror behind this primary mirror that reflects the light down into the base, into the bottom of the SLR, and this provides a number of functions that the camera uses for automatic anything. Automatic exposure, for example, is one of the things that is used in this light that's reflected down into the body, and also automatic focus. Both of these things are how these cameras are actually able to achieve this, or rather, because we have the secondary mirror, that is how these cameras are able to achieve this, these automatic functions on our behalf. This image here is based on a simplified film version. Back in the film days, before we had automatic exposure, before we had automatic focus, there was no electronics that could actually capture the light anywhere along the normal path, reflecting the light up into the pentaprism and through the viewfinder in order to capture the light and actually do some calculations on it, to figure out what exposure we actually need for it, or how we need to actually change the focus. All right, let me show you a couple other videos because there's some pretty cool ones. These are all somewhat old cameras, but all of these ideas stand. So before I even hit play, this is another digital camera, as you can see. This is another Canon. This is called the 20D. This came out in 2004, 10 years ago. That's crazy. This is one of my first digital cameras, actually, and I love this camera. But is there anything that you can notice that's different between this and the 5D? There's a couple of major distinctions. The size of the mirror is definitely much smaller. Let me see if I can also put up the 5D so you can see that one as well. Rewind this. So compare the size of these two mirrors relative to the size of this circle. That circle, that mount that I mentioned before, is the same size in both of these because the same lenses have to fit over both of them, but you can very quickly tell the difference in the size of this mirror. So what does that mean for us? Well, that means a couple of things. First of all, the image that we see in the viewfinder is probably going to be a little bit smaller, and in fact it is. You can also notice a difference in the viewfinder size itself. The viewfinder, or rather the pentaprism, the hump at the top of the body of the camera, is a little bit smaller in the 20D as well, just because there's less light that has to reflect up, and the viewfinder is inherently going to be a little bit smaller. But this also means something else that's very important, and that is that the sensor is smaller as a result. Now, we call this a cropped sensor because it is in fact cropped, whereas on the right we have a full-size sensor. This is the original full 35 millimeter size frame. In digital, we have these crop sensors, and we'll talk more about crop sensors at a later date. But this has a variety of things that impact us in that way. So let's see, does this actually work the same way? Does this mechanism work the same way? You can see both the primary and the secondary mirror flip up. The first shutter opens, the second shutter closes, and then the two mirrors flip back down. And now actually while watching these videos, hopefully you're getting a better sense of what I was saying before about why we have to have this separate mechanism, why we have to have this shutter mechanism to create the exposure on our behalf. And that is that mirror is bouncing around all over the place. When it slaps back down to the base of the camera, it bounces. It's probably letting in a little bit of light, maybe imperceptible, but still it's letting in a little bit of light underneath it. It's not going to be necessarily a perfect seal. This is just one of the reasons why this is not a good setup, or why it would not be a good setup to remove the shutter. Now here's one that is pretty special. This is a film camera. So let's take a look at what happens here. Notice, of course, that the mirror is larger. It does have a secondary mirror because it does have autofocus and auto exposure. First curtain opened, second mirror followed, or rather second curtain closes behind it. Did you notice anything kind of different about that, though? Did it look any different? Low shutter speed. So shutter speed is one of the things, but the color of the object behind the curtain was different. And the reason is that this is a film camera. There's no sensor. We removed the sensor, so let's look at it from behind and see the same thing from behind. We can see the action of the two curtains. Because the film, in the case of the film cameras, is the sensor, we could remove that out of the body and actually observe the mechanics of what's happening to the curtain itself. Now, what's really cool is a couple of things. I'm going to play it again, but I don't want you to look at the curtain. I want you to look at the viewfinder. Recall that I said that it's bouncing the light in front of the camera through the mirror, through the pentaprism, and then out the viewfinder. And what will happen when that mirror comes up is the viewfinder darkens. Then the curtains move, the shutter is opened, and then the mirror moves back down. And a bonus one for those of you that are film nerds, you can see the film advance as well, which is pretty neat. Okay, now there is that point that you had made prior is one that I actually want to bring up. We can see two different ways that the shutter itself is actually functioning. There are two modes, it seemed like. In this 5D video, the shutter looked slightly different. Let's see if we can identify the difference here. It's fast, so watch it. The first curtain's about to open, and then close right behind it. That looks a little bit different, perhaps, in some ways, compared to the film one. In the film one, we saw it expose the sensor, or in that case, the film, in such a way that it made a strip of light that moved down. It's not the case that the first shutter, or rather the first curtain opens and exposes the entirety of the sensor, and then the second curtain follows. It's that in order to make faster and faster shutter speeds, we sometimes we just can't do that. It's not mechanically possible in the case of the materials that we have to actually accomplish that. So we have a trick, and that is that we can have these two curtains just move down along the space of the sensor, exposing each of those parts to a fraction of a second as it moves down. So in other words, as the shutter speed goes up, there becomes a certain point where no longer can we open the first curtain completely and then close the second curtain. We have to open the first one, and before the first one is fully exposed to the sensor, can we begin to close the second curtain. This actually does have a name in the specifications of SLRs. It's called the X sync speed. The reason that it's called X sync speed is that the only time that you really notice the difference between these two shutter mechanisms, or these two functions of the shutter, is during flash photography. Imagine what happens when you take a flash of light during an exposure. It's very quick. Some of the fastest flashes that we have operate on the order of 32 thousandths of a second, 64 thousandths, 128 thousandths. Some of them go up to like 128 thousandths of a second, which is it's just cataclysmically fast. It's just so hard to imagine, especially compared to the 1/8,000th of a second that's possible out of these maximum shutters, the maximum speeds from these shutters. So what would that mean if we were taking a photo with this shutter, like this film one, that exposed only a portion of the frame when the flash actually fired? How would your image look? Right, exactly. So because the flash, if you're using flash, it's probably your primary source of illumination, which means that everything else is going to appear dark. If you took that same picture without flash, it will appear too dark. So that's the whole point of you using flash, unless you're, well, that's, all right, not exactly true. You may want to provide some fill flash. There's a lot of other reasons for it. But one of the primary reasons that at least I would want to use flash is if the room was dark and I wanted to take a picture of the room and to provide extra illumination for it. So by removing that light, all of a sudden this becomes dark. And by exposing only a portion of the sensor to the flash that was fired, do you get only a small fraction? Well, the fraction depends on the speed of the shutter. But do you only get a fraction of the exposure actually properly exposed in your final image? So X sync speed is sort of a fundamental limit in terms of flash firing. But even this has a little asterisk, and it is possible for us to override the X sync speed. How? Stay tuned. Later date. We'll talk about that. It is possible, but it's not by making the shutter faster. I will say that. So basically, this distinction is very important for us. We care about this, especially when it comes to flash. And this does actually matter. You might find that as you become more advanced in your use of photography, you might actually want to start using flash when there's plenty of light. And so you are then limited by the X sync speed, even if you're using flash in the middle of the day. Of course, we'll talk about more why you'd want to do this at a later date. But this is, in fact, a very important feature of cameras, of these cameras. One of the very interesting things is that you can imagine that for cameras that do not have this physical mechanism, do not have this physical limitation, and in fact use some sort of electronic means of taking the exposure, do not have this same problem. This is one of the reasons why SLRs have a slight disadvantage to some of these other styles of cameras that we talked about before. Compromises everywhere. Compromises. Yeah, these cameras will get you fantastic results, really good quality, very comfortable to use, just decades of battery life. But when it comes to using the flash in an outdoor setting, you might find that it is a little limiting. All right, so let's move on. Now, there's another feature of this that's pretty important, and we'll refer to it in a few times over the course of this class, and that is number 4. We talked about number 4, which was the location of the sensor itself, the location of the film itself. And many cameras actually tell you where that plane is in the camera. There is this symbol, this sort of knot symbol, this 0 with a line vertically through it, that appears on a variety of cameras, typically only SLRs, but sometimes other cameras as well. My mirrorless camera has it, for example. Other cameras where you would find this are typically ones where you can change the lenses, and otherwise you typically won't find this symbol. This symbol represents the location of the plane. If you imagine taking a slicer, a saw, and cutting your camera directly through that line, you would see at that precise location where this sensor actually is. Now, why does this matter? This matters for a couple of reasons. One of them is if you decide to make a lens of your own, as we've done here by 3D printing our own lens, it tells us something it provides to us some very important information about the lens that allows us to calculate some other aspects of that lens. ... Talk about more about that later. Little side note. Some people typically have asked in the past how much math is involved in this class. I think the most heinous thing that we do is some division. Don't really worry about it if you're not up to the latest calculus or anything like that. Really, it's high school level math at the most that you will need for this class. So if you can do that, then you're good to go for this class. Don't worry about that. Now, to come back to this idea, there's a couple of things that we might want to calculate. So it is actually possible, and one of the things that you will do later on is by determining how long this exposure actually took, you can actually figure out, because of the distance of the focal point to the location of the plane, you can do some math, do some division, do some addition, and some other stuff before you actually find out the size of the pinhole itself. You can find out just how precise I was able to make that pinhole with the needle. And as we'll probably find out, it's going to sound a lot more impressive than it is. It will hopefully be on the order of like 1/10 of a millimeter or 2/10 of a millimeter or something like that, but perhaps not. This is actually a new one. In the past, I used an old pinhole that had a 0.2 millimeter pinhole size, but I'm not so sure about this one. This one seems to let a lot more light in, which means that the hole is a bit bigger. Anyway, now this idea of having a lot of electronics and having a large body within a single lens reflex camera is actually pretty important. And if you were to tear apart one of these things, you would find out that really what it is essentially like a computer in the inside. There's a lot of electronics inside of one of these, and it's actually really neat to see all of the things that are inside. This image is one that comes from Digital Photography Review, dpreview.com, which, by the way, is a fantastic resource if you're looking for a new camera. They have very thorough, just extremely thorough reviews on a wide variety of cameras, and a lot of information and good forums and good glossaries for a lot of photographic techniques and concepts. But this tearaway of a camera does reveal to us a number of pretty neat features about this camera. I think Canon actually provides it to this website, as a number of websites actually seem to have these sorts of tearaway images. But we can see a variety of things. One of them is that we can see the primary mirror, the pentaprism itself. We can see the secondary mirror, and some of the mechanisms, the electronics down here. There's another little lens right here that focuses the light from the secondary mirror into the electronics down below to actually process the exposure and the focus. We can see the battery and the grip over here, some of the other mechanics. But one of the things that's really interesting about this as well is that if you open the mirror and if you open the shutter, there's nothing left protecting your sensor from the elements. And this is something that really matters to us as photographers, especially those of us that use SLRs or mirrorless cameras, because what happens is that we get a lot of dust. You might get a lot of dust on your cameras, and fortunately a lot of the modern SLRs have features that essentially shake it vibrates the sensor at a very rapid rate, trying to shake all of the dust off the sensor, and it's pretty effective, except that you've just moved the dust elsewhere, probably still within the cavity that housed all of this mechanism. So there has to be a way to sort of clean it. Now, I'm going to show you two slides. They're identical, except one of them has dust, and one of them has dust removed. It's not going to be one of those things where a scary monster comes out and scares all of you. But see if you can identify all of them. All right, here we go. So you're starting to see. It's just sort of going back and forth. How many pieces of dust do you see? 3? All right, so this has the dust. So the most obvious one perhaps is right here. It was so obvious that when I took the photo, I was like, this is really frustrating, but I didn't have any means of actually fixing it. Another one is right here, and a third one is down there. So it's annoying, but it's not the end of the world. Like I said before, a lot of the modern technology, this is now the fixed version, a lot of the modern cameras actually have anti-dust measures where it will vibrate. You might actually see it sensor cleaning or something like that, where it's trying to shake all of the dust off, and that's great. Also, there are a lot better techniques now than there were even just a few years ago for actually removing them. You might find like little blowers where you can blow puffs of air into the sensor to try to remove some of the dust. If you do find that you have a problem with dust on your particular camera, please do not use any liquids on it. That's just whether or not it seems obvious to you, it's a bad idea to not use liquids on your particular sensor. But also, as you can tell, I was able to fix this after the fact using software. How? At a later date. Yeah, that's right. We'll tease that. All right. Let's take a quick 5-minute break. When we come back, we will continue talking about SLR cameras and talk about the structure of the class. So stay tuned. All right, everyone. Welcome back. I checked my email for those of you that are watching at a distance, and I couldn't respond in time, but I want to answer one of the questions that I saw, and that is that, yes, we do hope to have sort of a live chat mechanism so that for those of you watching at a distance, it's not just a one-way dialogue, so that those of you can participate. Fortunately, right now, there's 2 things that are prohibiting us from having it in this lecture. One is, frankly, we're short on staff. We have we exploded with the number of people that joined this class, which is fantastic, and we thank you all for that. But there's myself, and there's one of the TAs, Shelly, and she's actually behind the camera right now, and so she's the one that's making it possible, along with Andrew, who's on our production team. They're actually making it possible to actually provide this stream to you. So rather than we thought that we would prioritize that first. So just as a matter of being short-staffed, we don't have someone to sort of manage the chat room. But also we were sort of finalizing the ideas of what chat room to sort of use. But we have, I think, decided on what we're going to use. So hopefully next week we'll have a better solution. But more on that forthcoming. Unfortunately for now, it will just be one way in this lecture. But hopefully by the next one we'll be able to have some sort of live feedback mechanism so that those of you can actually participate. And in fact, as we'll talk about in just a moment in this class, participation is actually an important aspect of this class as well, though it may be hard to understand from this first lecture, which is inherently, just because we haven't yet set up a collaboration between all of you guys and us, it is inherently sort of one way, but rest assured that future lectures we hope to balance a lot more between just this idea of lecturing and also getting to know each of you and actually presenting your own images as well. But again, more on that in just a little bit. So this is, I actually don't know what this is called, Rocket Air. But this is one example of a device that basically allows you to blow air into your camera and blow away some of the dust. It's pretty useful, and it looks like a rocket, so it's also pretty cool. So let's come back to this idea of SLRs. And so, like I said before, SLRs are essentially mini computers, or they have aspects of computation within them. And that is actually going to also be important for us. So one of the reasons that this class was classified as computer science in the past was because a lot of the things that we talk about, especially the idea of using editing software and talking in a little bit more detail about how the digital camera itself works, comes down to this idea of computation. And just to give you an idea, and in particular, an extremely brief history on digital cameras, and by that I mean 2 slides. There is this camera, which was created at Kodak back in the 70s, I believe. Unfortunately, I don't have the notes up. Stephen Sasson in 1975 created this digital camera, the first digital camera, and it's very unfortunate that at the time Kodak didn't recognize what they had created. As you now know, Kodak has now essentially shut down their digital camera business and, for the most part, their film business, and they just weren't able to keep up, which is really too bad because they were, of course, the leader for many years in film photography. But anyway, this is the first that we know of digital camera that was created by Stephen Sasson in 1975. Weighed 9 pounds. Compare that to your smartphone, which is a fully capable camera these days, and had 0.1. Let me make sure. Oh no, not even 0.1. 0.01 megapixels. So to give you an idea, that's 100 pixels by 100 pixels. That would be a tiny square on the space of your computer monitor. In fact, if you have an iPhone, it would be a tiny square on the space of your iPhone display as well. These displays have, I think, something on the order of almost 900 pixels or so by 600 or 400, something like that. So the screen on your smartphone has far more pixels than this original digital camera was able to capture. There's also an interesting aspect, which is that the exposure took 23 seconds. So this was not a fast camera by any stretch of the imagination, but as you know, it didn't matter at the time. That was an excellent first pass, and now we have fantastic cameras that look almost magical in comparison. Speaking of magical, check out these guys that Canon commissioned out of an artist to look at the future of SLRs back in the 80s, especially when I believe this was the 80s. Again, I have to look at my notes here, which aren't showing up on my screen. 1983, Canon decided to create this, and so they wanted to have something. They were thinking, oh yeah, digital cameras will be kind of cool. We'll be able to do something very interesting with the shape and design. And so they went with somewhat of an oceanic theme. Looks a bit like fish and rays and sharks, and pretty cool. But I don't know if I would use one of these particular types of cameras. Okay, that's it for the history of digital cameras. Now, a refresher about bits and bytes. So for those of you coming in, you have probably a variety of comfort and interest in knowing about computers, but there's just a few things that we really have to know that we can get to a baseline to be able to talk reliably about some of the aspects of digital photography. A bit and byte, for example, are the fundamental means of computation in computing. A bit is either a 0 or a 1. As you probably know, computers communicate in binary. They communicate entirely in electrical signals, either a low signal meaning off or meaning 0, and a high signal meaning either on or 1. So this is a bit, and everything that a digital camera does operates with these very basic fundamentals. It is all captured ultimately into a collection of zeros and ones. And how it is able to do this, we'll discuss more actually today. So we don't have to tease you too much about that. So we have a bit, which is either a 0 or a 1. We have a byte, which is a collection of 8 bits. So in other words, we have a bit, which is either 0 or 1, followed by another bit, followed by another bit, a collection of 8 of those. And that is also a fundamental aspect in computing. And 8 bits basically allows us to count up to a value of 255. So we can start with all zeros, then we can have 1, and then we can have 1, 0, and go on and on and on until we actually achieve our ultimate goal of 255. How is this actually possible? I encourage you, if you're not too familiar, to look up into it a little bit. We can talk a little bit about it right now, which is that since bits only operate in 0 or 1, the counting scheme is a little bit different than what you're familiar with. So we are used to base 10. Maybe it is no accident that we also have 10 fingers, but it just so happens that we can count in a very easy way with that. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And in fact, 0 is also a digit. So we would have this concept of 0 through 9. We have 10 separate digits in each one of those. And every time we go beyond that, we have to add an extra digit to be able to represent additional data beyond this. And this goes on in a very similar way for bits as well. If we can only count up to 1, if we can only have 0 and 1, that means that every single place for a number is not only just representing, like in our case, 10 values, but it's representing 2 values. So adding a single bit doubles the number of values that we can actually have. So if we have just 1 bit, we can have 2 states, 0 or 1, on or off. So that means we have a single bit, we have a piece of information that tells us either one of those 2 things is true. Now imagine that we have another bit. They can come in how many different combinations? 4, yeah. So we have 0, 0, 0, 1, 1, 0, and 1, 1. So with that, can we count from 0 to 3? So in other words, we have essentially, oh gosh, I didn't even realize we had all this extra stuff here. And again, please don't be put off. It's not, this is not math that we're going to be doing. We're not going to ask you to do conversions between binary and decimal or anything like that. So I just want to make sure that we have a very basic understanding of binary so that we can talk about some of these more advanced concepts, abstract away from them, abstract away from this idea just a little bit. So imagine that we have 1 and 0. We can actually imagine that this is, let's see, so if we just skip ahead some of the math, this is the 2's place, and this is, or rather, this is the 1's place, and this is the 2's place. And every single digit that we add beyond that multiplies that by some amount. So in other words, the takeaway is that by having 8 bits of these into a single byte, we have 8 of these bits. We have 2 values in the first place, 2 times 2 for the second place, times 2 for the third, times 2, times 2, times 2, times 2, times 2, to the 8th is 256. All right, that's enough about that. That's really essentially all you need to know. It's very interesting if you wanted to do some conversions between the two. Essentially, what is the takeaway here is that a single byte does have 8 bits worth of information, which in other words allows us to represent 256 distinct values. That is the main takeaway about this. Now, you might also be familiar with a lot of the prefixes that are associated with these ideas. For example, the kilobyte, or the megabyte, or the gigabyte, or the terabyte. These are all prefixes that denote how many powers or how many multipliers we actually have of these. So each of these are really powers of, or additional powers of 1,000. Kilobyte is essentially 1,000 bytes. A megabyte is 1,000 kilobytes, or in other words, 1,000,000 bytes. Gigabytes is 1,000 megabytes, or 1,000,000,000 bytes. So I apologize for those of you that are following along at home that know the proper English, the UK English, I believe me saying billion is not correct. Million might be the correct thing. Please correct me if I say that wrong. I'm trying to say it properly for everyone involved. And of course, a terabyte is then 1,000 gigabytes. So really, this is somewhat well known, I think. Especially, you might have an idea of the relative sizes between each of these prefixes and some of the other ones. You might know, for example, that a gigabyte is a lot larger than a megabyte. And in fact, we can be more precise and say that a gigabyte is in fact 1,000 megabytes. We can be more precise about a megabyte and say that it is 1,000 kilobytes, and so on and so forth. So if I have a kilobyte, for instance, which means that I have 1,000 bytes, how many different values can I then represent? $256,000, right, exactly. So I can represent 256,000 different distinct values. Now, that's oversimplifying it, of course. Usually when we're talking about a kilobyte, we're actually talking about a collection of bytes where each byte is actually allowed to do something different. A byte can be, for example, representative of a character. So for a character in a word. And so we might have 1,000 bytes, which might mean, in this case, that we have 1,000 characters. So there's a way of representing each of these bytes as different things. And this doesn't really matter, except to sort of place a little bit more concreteness behind this idea that we can have 1,000 of these different things in a byte, rather 1,000 different bytes, and a byte can be 256 values of any sort. And this will be very, very relevant in just a minute. Now, for those of you that might be a little bit more advanced, you might be thinking, wait a minute. This seems like an oversimplification. I thought all of these were multiples of 1,024. Well, yes, that is actually technically true, except that it's not. So this is actually what we had discussed before. These were the original sort of SI terms for these prefixes. The kilo actually meant 1,000 of it. So imagine a kilometer. It actually means 1,000 meters. Or a mega, or a giga, or tera, or so on and so forth. These are actually relevant, and these were actually in base 10. It just so happens that very early on in computing, all of this was co-opted by computer scientists to also represent this idea that we have bits and bytes, which are not in powers of 10, but powers of 2. It just so happens, and it's very convenient that this is true, that 2 to the 10 is 1,024, which is very close to 1,000. So they said, that's good enough, very early on in computing. And they just said a kilobyte is 1,024 bytes. But it's important to realize that when we're talking about these multipliers of 1,024, and again, this is for those of you that sort of already had this idea in your mind that it was, in fact, 1,024, there's a big typo here. Oh, gosh. All of these should be 1,024. I apologize about that. That was a copy-paste fail. So for those of you that sort of had this idea already that a kilobyte meant 1,024 bytes, that is, in fact, no longer the case. It's now been officially standardized in this standard at the very top, IEEE 1541, 2002, which, confusingly enough, was published in 2009, not 2002, that now a kibibyte is 1,024 bytes. So again, ignore that. It's 1,024 all along. And a mebibyte is 1,024 kilobytes, and so on and so forth. So what does this mean for you? Well, nothing. We're going to continue along with this simplification that a kilobyte is 1,000 bytes, and that a megabyte is 1,000 kilobytes. This is not, in fact, a simplification. This is, in fact, the more correct way of doing it. There's also, so my main interest is in computer science, and I will geek out endlessly about this stuff. But it's also very interesting that hard drives for the longest time used this base 10, whereas the computers use the base 2. So there's, for the longest time, if you bought a hard drive that said that it had 1,000 gigabytes, or rather that said that it had a terabyte in it, and then you opened it up and it had 900 gigabytes, and you're like, why did I not get my full 1,000? And it's because of this confusion, that there's this decimal system where they were using, the hard drive manufacturers were using this proper method, proper, quote unquote, for using these 1,000 prefixes, whereas all of the computers were using powers of 2. They were using this 1,024. So now modern computers, modern Macs especially, will actually make the distinction between the bases and show you the correct thing accordingly. So the takeaway from here is to remember the normal SI prefixes, and this will matter for us. And it really, ultimately, this is going to matter in terms of really just for scale. Just kind of remember that a gigabyte is 1,000 megabytes, and a megabyte is 1,000 kilobytes. That is really the simplification that we can take away here, and that it will be used in this class. So any questions on that before we move on? Again, if you have additional questions about binary, I encourage you to look online about that, but that's not going to be really the most important aspect of this class, which is why we just blistered through the description there. Now, why is this important, though? Why did I actually spend some time describing this for you, especially in the first lecture where you're like, oh my gosh, what is all this stuff? Powers of 2, powers of 10, 1,000 versus 1,024. The reason is that all of these images that we're recording are, in fact, recorded with these bits and bytes. So what would happen if we actually zoom in on one of these images is we see that it is made up of a collection of essentially pixels, of these small squares, each one of which is a pixel. And each pixel has some information associated with it. So there's a lot of information that's stored here. We might want to identify a specific pixel by thinking of this as a coordinate plane. And so in other words, we actually want to identify the pixel that's 300 rows across and 200 rows down to identify a specific pixel. And within that pixel, there's additional information as well. In this case, it's the color of that pixel. Each of these pixels that in combination make up our image, when you break them apart, actually are made up of individual pieces of information that allow you to figure out what that color is for that pixel. So why is this important to us? The reason that this is important to us is that it allows us to talk in a better way about the different formats for storing these images. One of them that you're most likely familiar with is the JPEG file format. Now, computers, in order to create the color of any particular pixel, does it with three primary colors. In this case, or in all cases with computers, it's not the primary colors that you might have learned in grade school. It is the primary colors of red, green, and blue. And if you had a magnifying glass with sufficient power and looked at your screen or your smartphone to zoom in on that and actually see each of the individual pixels that make up your screen, you would actually see that every pixel is made up of a red component, a green component, and a blue component that are illuminated at various intensities to create, in combination, the color in the end. So the technology that we have now doesn't allow us to recreate a specific color with a single piece of hardware. We have essentially just a red light, a green light, and a blue light that we vary in brightness and combine to actually observe the colors that we see on our screen and on our projectors as well. There's pretty much all of the technology that we have that actually displays colors uses a mechanism similar to this. And your printer might be a little bit different. You probably are familiar with the same idea. If you have a color printer, you have different toner, you'd have different ink colors. You might have maybe not red, green, and blue, but perhaps you have black, magenta, yellow, and cyan. There's a variety of different colors that printers can use to actually create these, but in computers and displays and smartphones and projectors, it's almost universally red, green, and blue. So this means that if we're going to keep breaking this down to figure out how we can display an image on screen, I am saying that we can define each pixel with a combination of values, a red value, a green value, and a blue value. So imagine for just a moment that we have one bit of information for each of these colors. Imagine that we allow red to have one bit of information. We have green to have one bit of information. We have blue to have one bit of information. We have essentially 3 bits of total color information for one pixel. That means that we have for each of these 2 states, either on or off. So imagine what would happen if I had red as a 1, meaning on, green as a 0, meaning off, and blue as a 0, meaning off. What color would you imagine my computer would display? Full-on red, bright red. And that's it. There's no other red that I can have. I can't have any sort of gradient of red. I can't have a darker red. I have either red or no red. So I could likewise turn red off, have a 0 here, a 1 here, and a 0 here for blue, a 1 being in green. We would have full-on green, and so on and so forth. So you might say, okay, this is not going to work, obviously, for photos that have lots of gradients, lots of color variations that allow us to reproduce pleasing quantities of colors. So how can we affect this? How can we actually create this? The idea is to just use more bits, throw more bits at the problem so that we can represent more values of red, more values of green, and more values of blue in our file type. And typically what you will see, especially in JPEG, and what is common for the vast majority of file types out there that we will use, is that each one of these is provided 8 bits of information. What is 8 bits again? A byte of information. This again is that fundamental piece of information. So we have 3 bytes of information for every single pixel represented on our screen. This means also that the red portion has how many different discrete values? How many different reds can we display? From off, which would mean black. If we have no red at all, if we're only talking about red and we have no red at all, that means it's off, that means it's black. All the way to full-on red, a value of 255. Did I just give it away? I just gave it away. Whoops. Well, that's one case where I didn't have to tease you guys. Anyway, we have 256 discrete values that we can actually represent, where at the maximum, 255, that is full-on red. But we can have gradients of the two. We can have one value that's 255 in red. The pixel adjacent to it can be a value of 254, 253, and so on, all the way down to 0. We get this lovely gradient from red down to black. This is what allows us to create all of the various colors, especially when we combine each of them into a single pixel. Now, you can imagine that it might get we might be able to represent a wide quantity of colors by actually combining each of these. And in fact, we can. Having 24-bit color means that we can represent on the order of millions of colors, millions and millions of colors, just by multiplying 256 reds times 256 different greens times 256 different blues. We get millions and millions. I think it's 16.7 million different colors. So we have, in essence, an 8-bit file. The reason that it's 8-bit, or an 8-bit image type. The reason that it's 8-bit is that each one of these channels, the red channel, the green channel, and the blue channel, are provided 8 bits worth of information for a total of 24 bits. Now, some files can actually present more information than this. You can imagine that if you want to have a really very smooth red gradient, you might need to have more than 256 discrete values. You might be able to, if you were to just have a long enough gradient of just pure red all the way down to black, with only 256 variations between that, you might be able to actually tell the difference from one to the next. In fact, this is true, and this is going to be important for us at a later date. But there are also other types of files that overcome this issue. For example, TIFF files. They do come in a variety of bit depth, which is another way of saying the number of bits that we can represent at every single color channel. But in this case, we're talking about 16-bit TIFFs, which in essence provides 16 bits of information for the red, the green, and the blue. Now again, to make clear, saying that we have 16 bits of information doesn't mean that we have twice as much data. Oh, no, no, no. This means we have 256 times 2 times 2 times 2 times 2 times 2 times 2. It's times 2 times 2 to the 8 more times. It is an exorbitant number of colors that we can now represent with this information. So for the vast majority of cases, especially when we are talking about transferring images around from myself to my grandmother, for example, when I want to send her an image over email, I probably want to use something that's acceptable but not exorbitant, because if I have to have all of these different values to represent colors, which might be good enough in the JPEG, and as you know, JPEG is certainly good enough for almost all cases that we want to represent images, then I would just be wasting bits. I would just be making the size of my image larger, because by necessity, every single pixel will have this much information, thereby making the size of the file that much larger. So let's do sort of a little thought experiment and imagine that we have a JPEG image. And in this case, we are really conflating the term of what a JPEG actually is. There's a lot more advancement that goes into this. Now, keep in mind that all of these types of images we can classify as what are called bitmap images. In other words, for every single location, we can provide a certain number of bits that dictate the color for that particular pixel. And almost all images that you have will be bitmap types of files. Other types of files are vector files, where shapes are defined by mathematics, for example, which would allow you to zoom in sort of infinitely on that. And because it's defined by mathematics, you can get a very smooth curve, zoom in, and you would never see this pixelation problem that we see here. But in the case of digital photography, that doesn't matter. Almost every image that we're going to deal with will be bitmap, and so we're going to not really worry about vector graphics. So to think about this idea of what, unless we do something about the size of this file, let's assume that we have a bitmap file that's 2 pixels by 2 pixels. So we have a grid of 4 pixels. And I claim that I'm going to save this file as an 8-bit file, or in other words, maybe a 24 total bit file. So in other words, each one of these pixels has how much information? It has a red component, a green component, and a blue component. Red, green, blue. And how much do each of these colors have in terms of information? 8 bits, or 1 byte. So in other words, the combination for each of these is 3 bytes. This is just like we talked about before, nothing new here. 3 bytes for a single pixel, which means that for our 2 by 2 pixel image, we have 1, 2, 3, 4 times 3, 12 bytes of total storage on our computer. That's not so bad. I have a terabyte of space on my computer. That doesn't matter at all. Okay, fine. Now let's talk about a much bigger image, like say 10 megapixels. 10 megapixel image is probably something on the order of like 3,000 by 2,500 pixels or something like that, 10 million pixels, 10 megapixels. Again, there's that prefix. This is the SI prefix, not the funny mebi pixels. We're talking about 10 million pixels times 3 bytes at every single pixel. Every single pixel has 3 bytes of information. Now how big is my file? 10 million times 3, 30 million, so 30 megabytes. So that's kind of big. So for those of you like me that used floppy disks back in the day, those were 1.44 megabytes in size. We would need 30-ish of these, high 20s, mid 20s of these floppies just to store one of my 10 megapixel information, one of my images that is made up with 10 megapixels. That's a lot. This can't be. Can't all those smart computer scientists, not me, but can't all those smart computer scientists figure out a way of actually compressing this down, making them smaller? In fact, yes. There's a variety of compression techniques that allow us to shrink the size so that if you look at an image, so for example, a JPEG image isn't 30 megabytes when you have a 10 megapixel image. It's something on the order of like a megabyte or 2 or something like that. That's a phenomenal rate of compression. That's amazing. There's a variety of types of compression that allow this to happen. One of them is, so let's think of a couple of different ways that we could do this. Let's say that I have these very simple images of flags. I have the German flag and the French flag. So how can I compress these to reduce the amount of information that I actually have to store on disk? How would you, if you actually had to communicate with someone what this looks like so that they could reproduce it, how would you do that? You probably are not going to say, okay, first pixel, black. Second pixel, black. Third pixel, black? No, what would you do? Give me some ideas. Yeah, I like that. So you could reduce it by segmenting it. You could, in this case, say all pixels in the top segment will be black. All pixels in the middle segment will be red. All pixels in the bottom segment will be yellow. Now, this means that we have to, in order to tell a computer what a segment is, we have to be more rigorous in our definition of a segment. So what are several different ways that we could actually define this? So we could say, for example, the top third of the image. So a segment is a third of the image horizontally. And then another segment is the second third. And then the final segment is the third third. Now, in this case, we can think about it slightly differently. Imagine that we do this by row. So the very top row, the first pixel is black. Now all subsequent pixels are also black. Second row, black. Subsequent pixels are all black. This is pretty simple, and this would allow us to segment it a little bit more in a little bit finer scale so that we have some control over the amount of compression versus how much we can express in the file. Now imagine that we apply that same mechanism, that same method, to the flag on the right. So the algorithm that we had just proposed was take a look at the first pixel. We're going to look at it by row. So the first row, the first pixel is blue, followed by about a third of the row is going to be blue, and then it's going to be white, and then another third of the row is going to be white, and then the final third will be red. And then for the next row, it will be the same thing, and then for the next row, it will be the same thing. So imagine that we were storing this on a computer. We use this compression mechanism to actually reduce the size of these images. How much have we reduced them? We've reduced them quite a bit. But is there a difference in how much reduction has occurred from one image to the next? Who thinks that there's a difference in how much space is saved in these two images, if they're the same number of pixels? Any difference? Okay, so is there anybody who thinks there's no difference? Does anybody have any opinions? Okay, let's try this again. Who thinks there's a change? Okay, who thinks there's not a change? Good, okay, so we have a pretty even breaking point between the two. Now, the answer is that there is, in fact, a change. And the reason for that is that we have to represent this data by row. So we're going to have the same number of rows in each of these, but in the case on the right, for every row, we have to change the colors twice, so we have 3 times as much information. So we have the top row, whereas on the left, we could say the top row is all the same color. Second row is all the same color. Third row is all the same color. In the one on the right, we actually have to say top row is all the same color until this point. Then it's this color, and then it's this color. That's 3 times as much information. Now, this is not actually a good compression mechanism for images. It's very great, and by images I mean photographs. This is fantastic for this sort of image where it's very simple colors. In fact, this is precisely the type of compression that does occur in a particular file type, and it's one of the primary reasons why that file type is just not good for images. Imagine that we apply this same compression, what's called run length encoding, because you're running across the row trying to figure out how much of a run you can actually encode with this information. Imagine we try to apply this to an image, or rather a photograph, that has gradients, that has slight variations in the red from one pixel to the next. Well, all of a sudden, this breaks down because it's not the same red. You have to say, okay, this is red number 1, this is red number 2, this is red number 3, and you can't compress it down any further than that. So if we take this image on the left, we have a solid, it doesn't appear this way, but assume that we have a solid blue background with a red apple that has these nice smooth gradients. We can only compress it to the one on the right, where the first bit is blue, and then we can say, okay, the rest of this row is blue, but once we get to the middle of the image, we can no longer do that simplification. So we reduce the amount of compression that we can do on this image is vastly reduced. We still have to store an enormous amount of information comparatively relative to this. So this isn't going to work for photographs. The other types of mechanisms that exist, take a look at photographs in terms of blocks. So there are many different schemes for compressing this, but what we just described was a mechanism of compression called lossless. In other words, we can, after encoding, after actually compressing this down to some other file, we can reopen this file and have absolutely no loss of information. We are able to recreate precisely the original image that was described, which is great. That sounds wonderful. That sounds like a property that I want to have for my photographs. But sometimes having this lossless compression means that we have to actually recreate all of these things precisely as they were, and we can't have as many mathematical simplifications. We can't make some assumptions about various things that allow us to simplify the image even more and allow us to compress it even more. So take a look at this image. This is an actual photograph, as you can tell. I've zoomed into the same portion on this fellow's face in the upper left-hand side. On the left, this is the original version, uncompressed, so to speak. And on the right is a highly compressed version of the same thing using the same compression technique that JPEG uses. JPEG, unlike the compression technique that we had just talked about a moment ago, is in fact a lossy compression technique. That means that some data is thrown out in order for us to get these very nice small file sizes. Now, many times you can't notice that, and that's because the assumptions that they make and in their compression work very well. But when you really dial it down and you really want to compress it a lot more, we can infer a little bit about what is actually happening in the image. So take a look in this right side here. You can tell, like what I alluded to before, hopefully you can tell, it might be a little bit small, especially if you're at a distance, is that this image was broken down into blocks of some number of pixels. It looks like it might be about 16 pixels or so, usually powers of 2 or what these algorithms would operate most efficiently on. And then each of those were simplified in some particular way. So even though this background was of some bushes, it is actually simplified that to some sort of gradient representing the colors that are represented there. And there's a lot of assumptions that are going into this that actually work based on the human visual system. So a lot of the reasons that JPEG is able to work so well is that it basically just tricks us into thinking that we are seeing the same amount of detail. That's not exactly a precise way of saying it, of course. There's some oversimplification that's happening here, but they are making assumptions based on the way that we perceive images in order to use that to its advantage and throw away additional data. So lossy compression, again, it's one of those compromises. Lossy compression is a great way for us to reduce the file size even more by making assumptions about how we actually view the image, simplifying the data that we can actually store in the file, but thereby throwing away some data at the same time. So what does this allow us to do? We can now talk a little bit more about some of the different types of files that you will probably encounter in your career as a digital photographer. Of course, there's JPEG. So lossy compression, 24 bits worth of color. There's one thing here that we haven't really talked about yet. It's this final column in this file type slide, which is alpha. Alpha is basically just a fancy way of saying transparency. Does this file support transparency? And why would you want transparency? Well, imagine that you have, so all of these files, all images on your computer, on the web, are square. But imagine that you want to put a button on the web that is actually round. How can you do that? Well, you can create a round object in your image and then make the corners transparent. So JPEG does not support alpha, it does not support transparency. That's fine. The vast majority of our images are, in fact, rectangular. GIF, on the other hand, lossless, and in fact, GIF, the run length encoding compression used in GIF is the one that we just described, that we just talked about when we first started talking about this just a few moments ago. Its compression is, in fact, lossless. So that's great. You want to store your original data in a GIF file? Well, don't do that, because unfortunately, you are allowed a maximum of 8 bits for every pixel. This isn't even describing red versus green versus blue. This is 8 bits total. How many values is that per pixel? Pounding this point home. Same one. It's a byte or 256 different values. So what I'm claiming is that in a GIF file, yeah, it's great because it's lossless, but you can only represent 256 discrete colors. And that, again, is a little bit of a white lie. This is out of a palette. It's basically a GIF file you can think of essentially as a computerized paint-by-number system, if you remember those as a kid. For those of you that don't know, they're at a distance and didn't have the luxury of going to Walmart or whatever, or McDonald's, and getting one of these as a kid. It's basically the outline of everything has been drawn, and it says paint color number 2 here, and then you paint it, and then you can actually see your final result there. That is essentially a palette of different colors that you have. So in a similar way, in the GIF file type, do we define out of 24 bits, or out of 16 million different possible colors, we take 256 out of those for one file, and then we paint by number. So we say this pixel is color number 1, this pixel is color number 4, this pixel is color number 5. So it's not as bad as just having 256 fixed colors, but still in the vast, vast, vast majority of our photographs, we have way more than 256 photos. So GIF is out. Don't use GIF for photos. It's not necessary. Okay, another asterisk. Unless you want to have one of those fancy, like dancing hamsters. Remember dancing hamsters? Or the more modern, like the animated GIFs that you find all over the internet nowadays of simplified. They look like simplified YouTube videos. There's something off about the color. What GIF does support that these other file formats do not is that you can have animation. So even though you have this vast reduction in color, you can also have animation. So there's that. But for our purposes in this class, we're not going to be doing animation. We're going to be talking about digital photography. So GIF is no good for us. PNG, on the other hand, is lossless, is 24-bit, and does support alpha with an additional byte. So rather than have 3 bytes of information for an individual pixel, we have an additional byte, 4 bytes of pixel information at every pixel. That 4th byte denotes the alpha, which is kind of great because then we can have a sort of a gradient of transparent to not transparent. It's pretty nice. It's a pretty nice format. But of course, because it's lossless, its compression does not provide files that are as small as JPEG. So that's, again, one of the compromises. Lossless compression means, by definition, that you're going to have larger files. PSD, these are Photoshop files. The compression is not really known because it's a proprietary file type. It is not open, but we can gather some information about it. Most likely it is lossless because they do not actually, I imagine that they would want to preserve as much information about your file that you're working on as possible. And there's also evidence that shows that it is in fact 48-bit, and obviously it supports transparency as well if you have multiple layers. And we'll talk more about Photoshop at a later date, just as you've come to appreciate in this class. TIFF, like we just talked about, is lossless, 48 bits, and has no alpha capability. For our purposes, we are going to mostly be working with JPEG for the vast majority of cases. We will be working with TIFF occasionally later on in the class when we really start to realize the power of raw file formats out of our cameras and all of the additional color latitude that they provide that we cannot get in JPEGs. So keep these in mind. And all of this information, by the way, will be, and by information I mean these slides, will be posted onto the course website. So for those of you taking notes here and at home, don't worry about writing down the contents of the slides themselves. I will provide this as a PDF online so that you can go back and refer to it if you'd like. So let's talk a little bit about the content and structure of this class. If you've seen the course website, you may have seen already the schedule. Today is week 1. Welcome. And in subsequent weeks, we will start talking about exposure. And this is relevant to more than just digital cameras. It is relevant to film cameras. It is relevant to camera phones. It is relevant to any device that essentially takes a picture. There are fundamentals to photography that are consistent across all of these devices that capture images, and we will be talking about those. Really the first 3 weeks or so of this class, for those of you that come in with an existing background in photography, don't just ignore it. We will be talking about a variety of things that will hopefully either fill in some gaps or hopefully patch some misconceptions that you might have picked up from related to each of these. But for those of you that are new to photography, this is going to be the great way to slingshot you into experience with how to manipulate your camera and deal with the compromises that your camera actually causes for you. Follow that up by optics. We'll talk a little bit more about lenses. The histogram. If you know what a histogram is, you might wonder why we can talk about it for an entire lecture. Just wait. It's awesome. Software tools, digital cameras. We have 2 lectures on digital cameras where we talk about the sensors themselves, the different types of sensors that exist, what the differences are, some of the distinctions between this concept of cropped sensors versus non-cropped sensors and what that means in terms of the physics for everything that we had seen prior, the optics, the exposure, how this actually impacts the way that the camera behaves and how you can interact with the camera as a result. Color and artifacts. Color is actually really important. If you've already, and hopefully as you've gathered by now, we're just representing color with numbers. So really a computer in many senses of the word is really just the paint by number system. It says that at this particular pixel I want to display white, but what does white actually mean? It has different meanings to different computers, to different cameras, and we'll find out and talk more about this later on. Then we'll talk about how we can actually expand your newfound expertise into other areas as well. So what we expect out of you is that you watch or attend lectures. There will be 1 final project. All this information, again, is repeated on the course website, which I'll provide in just a moment. 4 projects, 5 problem sets. The first problem set is going to be pretty relatively lowball. It's going to be really a setup problem set and maybe getting to know each other and starting some of this collaborative effort. And I think some of the aspects of this class that are really powerful are, yes, perhaps the lectures where really it's just me talking about digital photography and all of these aspects, but photography is more than just the technical aspect as well. It's this artistic side. And so rather than devote this entire class to just the technical aspects or devote the entire class to just the artistic aspects, we've divided it into a couple of different things. The reason that watching the lectures is important and doing the problem sets is important is because that allows you to get a sense for the technical aspect of this. But the projects, the final project and the critiques are going to be the best way of actually providing your work to us and to others, and we'll talk more about this, so that you can actually improve the creative side, improve the artistry behind these images that you are striving to achieve. So this is actually an important point, is that whether you are here in person or at a distance, one of the things that we really would like to do is to make this, and I really want to be careful using this word, make this a little bit more social. Not in the sense of like social media, but really make this collaborative effort between you amongst yourselves and you with us, with the staff, so that we can improve each other's photography. And one of the first critiques will in fact be my images, where you can sort of give me ideas about what I'm not doing right, what sort of things would be improved. And in fact, I should change that. I should strike through saying what I'm not doing right, because all of this is meant to be very constructive. It's meant to be when you are displaying an image, when you are participating in a critique and you decide to show one of your images, even if you think it's one of your best photographs, you will still have a bit of nerves. You'll still be worried about someone not liking it, about what people will say or how they will say that. And that is something that's very, very important. We do not want negative comments about these images. And try to imagine the work that people have put into their images. Really, this is meant to be a positive experience and to try to improve your photography and to also have a say into helping other people improve theirs. So essentially what will happen is that not this first week, but starting subsequent weeks, we will have critiques where you'll basically take photos, and they can be probably related to your projects or maybe even just photos that you've taken. But ideally, they are photos that you capture that are new, not ones that you've taken in the past. Perhaps there will be an exception for the first week where you can show us sort of your best images, so we can sort of get a sense of what sort of photos you like to take and what you think of your own work and that sort of idea. But really, subsequent to that, we're hoping that you will take new images and decide on about one or so a week that you will post to a website for others to view. Now, that doesn't necessarily mean that every photo is going to get critiqued. So one aspect of this that is also important is that participation aspect, and that hopefully you will be presented with the opportunity to actually present in class in some way, even for those of you at a distance, one of your images on screen, and we'll talk about it for just a minute or so. And subsequent lectures, like I said, will hopefully be reduced in time so that we can actually have this critique portion, so that we can have more of a discussion in person and with those of you that are joining us at a distance, but it will have to be a live discussion for that. The critiques can happen asynchronously as well, and what I mean by that is that you can participate in the critiques most weeks not live. You can do it sort of from the comfort of your own home, but as you will find out in the upcoming weeks as we talk a little bit more about critiques, there will be one point in time where we hope that you will be able to display your image in class and actually get live feedback on that, and then everything else can be done at home. So more details about this to be fleshed out, but again, the important parts are that you'll have once weekly critiques due, in other words, one image due every week that you will submit to a website that will then be sort of viewed by everyone. And really the main motivation behind this is twofold. One, to get you practicing with digital photography. We can talk about photography all day, we can talk about the theory behind it. The way that you will really improve is to actually do it. So this is really to motivate that. And yes, the projects do have photographic components, the problem sets do not. But the way to get you to consistently be doing this is hopefully by taking photos on a weekly basis, and not just, by the way, of your cat, even though cat photos are encouraged occasionally. Spread it out. Have some unique submissions every once in a while. And the second idea is also to get ideas from other people, to talk about the artistic aspect. For those of you that come into this class with more of an artistic rather than technical background, we're definitely going to hope that you will participate in these critiques and provide a lot of information. My background is more technical than artistic, so we may speak a different language. We may use different words, but you may be able to talk about these things in more succinct, or maybe even express them in a better way than I can. So that's why I think this will be very successful, hopefully as a collaborative effort. Now, the course website, if you haven't seen it yet, is digitalphotography.exposed. It's sort of a clever play, obviously, on the name of the class, Exposing Digital Photography. If for some reason you have a restrictive firewall at your workplace that blocks .exposed, you can also try, though it may or may not work, you can also try dme10.org. They're synonyms for each other, but basically digitalphotography.exposed is our website. Staff@dme10.org or staff@digitalphotography.exposed is the email for the staff. That's including myself and Shelley, who unfortunately we won't be able to introduce for those of you watching at a distance because she is filming right now, but maybe would you be able to come say a word or next week? Sure? Yeah, okay, come on down. Yeah, you can just lock it, maybe tilt it down a little bit. Anyway, Shelley is our TF. However, because of our fantastic enrollment, last I checked it was 70-something, we will have to increase our staff because the load will just frankly be too high for the two of us. So this is Shelley. Hi, Shelley.
Hi, I'm not mic'd. Sorry, Andrew.
Oh, yeah.
I'll just stand close. Okay.
Want to introduce yourself?
Yeah. Hi, I'm Shelley. I took this course in 2011.
Yeah.
2011. Yeah. It was actually one of the first sort of photography video courses that I ever took. And now I do it professionally, which is pretty awesome. My husband and I are team photographers. We're doing our first wedding this fall, which is terrifying, but it's a lot of fun. And yeah, I'll be around. I'm always behind the camera for lectures, but for whatever we decide to do for sections, online, I tweet a lot. Follow us on Twitter. Yeah, it'll be good.
Great, thank you. So like I said, hopefully Shelley is our first TA. Hopefully we'll gain some additional ones as well to sort of help with that load. And they will also be included on the staff list. Right now on the staff list, Shelley and myself. And we also have a staff Twitter, Expo Digi Photo. And we've tweeted a couple of things, most notably the URLs. Basically, any announcements that we have are going to be posted to Twitter. We'll also send important announcements also to the email, so don't worry. If you are not a user of Twitter, you won't necessarily miss anything that is vital, but we will post some stuff that we just sort of find. It's meant to be a little bit more casual of an experience on our side. If we find sort of a neat photo link that we want to post, we'll probably post it to the Twitter account or something like that. And again, major announcements will go out also to the email list. If you're registered for this class and you did not receive a welcome email from me this morning, please send me an email and let me know. We should try to get that organized as quickly as possible. We will have optional sections that we will talk more about in the upcoming weeks, but as part of Problem Set Zero, which will be released tomorrow or Friday, and again, it's going to be relatively easy, you will complete a survey that will help us figure out what the sections are actually going to look like. And the sections will most likely be much more collaborative than lectures even will be. Or maybe they'll even be a little bit more fun. Perhaps for those of you that are just happen to be local to us, we may try to do some photo journeys, go around town, do that sort of thing. We'll see. We'll see what it's actually going to look like. But hopefully it will be fun, collaborative, and informational for everybody. And with that, I want to thank you all very much for coming. I hope to see you again next week as well. And until then, have a great week.